Hello everyone. Today I'm going to walk you through how scanners work both in theory and practice. Before I begin, I'd like to explain the meaning of scanning and lexing. Back in the day when computers were slow, scanners referred to the process of loading source code from disk to memory, and lexing referred to turning source code to tokens. But today computers are really fast, so those two terms are used interchangeably. As a motivating example, let's consider a simple program to compute the factorial of a number. Obviously, the program on top will run successfully, but the program below will throw a syntax error. So how does the scanner know that the program on the top is valid and the program below is invalid? To answer that, we have to look into theory. And unlike other parts of computer science, there's a strong connection between scanner theory and how scanners are written in practice. So if you ever read a book about scanner theory, you can easily understand a scanner in production. To identify the syntax of a valid program, we need to first specify the syntax of the language. To do that, we use regular expressions, which are built using three simple operations: alternation, concatenation, and clean closure. To explain those rules, I'll walk you through some examples. The first expression, hello, is an example of concatenation, as the first character is concatenated with E, then L, and finally O. This expression produces the string hello. The next expression is an example of alternation. The first and last characters are D and G, but in between those two characters we can have either O or I. So both the strings dog and dig can be produced from this expression. Next we have an example of clean closure. The first two characters are M and O, but the final O can be repeated 0 or more number of times. The postfix star operator says the character before can be repeated 0 or more times. The set of valid strings for this expression is infinite. The next example is also an example of clean closure, but here the entire string moo can be repeated 0 or more times. So the empty string and moo repeated any number of times are all valid strings. The next expression is an interesting one, as we have both alternation and clean closure. Here the clean closure has higher precedence, so the expression will first expand to any number of B or A and then choose one character from B or A. This explains why we are able to match A, B, A, as shown here. Oops. Finally, a more practical example to match natural numbers. A digit can be any character from 0 to 9 inclusive, and non-zero digit can be any character between 1 to 9 inclusive. So a natural number is defined as a non-zero digit concatenated with 0 or more number of digits. An important thing to note here is that regular expressions work on any characters, and they don't care about the meaning of character 0 or 1. So now that we have specified the rules of the language, we need a mechanism to identify valid strings of the language, and for that we use a deterministic finite automaton. This is a DFA to match the character A. State 1 is the starting state, and the double circle state is the accepting state. This is a DFA to validate the string hello. As you can see here, the DFA will reach the accepting state only after processing all the characters of the string hello. If the string had any other last character instead of O, the DFA would not have reached the accepting state and the string would be invalid. This is a DFA to match both dog and dig. From the starting state, the DFA will proceed to state 2 only if the first character is D. Then it will consume O or I, and then finally consume G to reach the accepting state. Here we can see the alternating rule is implemented in the DFA. Finally, this is the DFA to identify natural numbers. It first consumes a non-zero digit, then consumes 0 or more number of digits. It reaches the accepting state right after consuming a non-zero digit because the number of digits can be 0 or more. This brings us to the end of theory. As you just saw, regular expression is used to generate valid strings of a language, and DFA is used to validate strings. In other words, it is used to check if strings belong to a language. It can be proven that both regular expression and DFA are equivalent, but there is no one-step algorithm to go from regular expression to DFA. We first have to convert the regular expression to NFA and the resulting NFA to a DFA, and finally convert that DFA to a minimized version of it. That's all about the theory, and now we can see how a scanner is implemented in practice. A scanner is just an implementation of a DFA, which means a DFA and the scanner are the same thing. So this is the code to scan a character A. We first peek and see if the next character is A. If that condition evaluates to true, we consume it and pack everything into a token. And as I said before, you might see a strong connection between the DFA for identifying A and the scanner code to match A. Next, we have some code to scan natural numbers. We first check if the next character is non-zero. If that's true, we consume it and consume rest of the digits if any exists. Finally, we pack everything into a token, and once again, here also we see a strong connection between the DFA and source code. That's all I have to present, and thank you for watching.